Alrighty then, happy Tuesday afternoon. We have a couple of administrative things to take care of today, and I'd like to start by making the first announcement. Do you have any questions before I launch into this? Okay, the first announcement is we're shifting TAs. Liz unexpectedly, unforeseenly, and uncontrollably has had to put a higher priority on some other things than her ability to be a TA in this class. And we'll miss her because she's done a good job keeping me organized. We do have a replacement, however, who didn't know anything about this class not very long ago. I'm going to ask him to introduce himself and explain that because of this rather sudden thing, he actually won't be able to be in class on a regular basis because he will be taking another class. So at any event, please introduce yourself and give us a little background, please.
Hello everyone, my name is Saber Khanduzi. I'm a first year PhD student
Step into that.
Okay. I'm a first year PhD student at University of Cincinnati in Department of Geosciences. I have the opportunity to be the GTA for this course, to collaborate with Professor Lovell in this course and help you if I have any knowledge in this regard. And you can contact me with this email, and my office is 613. Whenever you contact, we could set a time and have a meeting or reply to your email to solve your problem. Okay?
Okay, any questions before he goes to his class? Max?
So I know I joined this class after everyone else.
Right.
So Liz was helping me.
I know, and I have you on my list to chat with. Can we talk right after class?
Yes.
Thank you. Okay, thank you, and we'll see you.
Can I do
Excuse me?
Can I do the for the next class or
I'm sorry?
can I leave now?
Yes, no, yes, go. Yeah, go.
Okay. Okay,
Take
thank
care.
you very much. Goodbye.
Second administrative thing, we're a quarter of the way through the term. We've done 2 of the 8 units that we want to do. It's time to look at grades. Keep in mind, this is a cumulative points. We add points, you don't start with anything, you keep building them for all of the activities we do. So at this point of the term, this is a distribution that looks fairly normal. Remember that this is the distribution for 2 sections. And I'm not at all surprised by the distribution here. We have people who really haven't formally, unregistered or dropped the course. We have folks that have missed 1 or more assignments. And for some of those people, they'll probably end up dropping, and that'll sort itself out. Most of us fall into this category in here, and by and large, that's normal. And then because we've gotten bonus points, we have one person who's got more points than theoretically have been awarded or possible. I would hesitate to say what's happening, but I'm pretty confident that everybody in this category will be fine in terms of grades. What I would point out is if you start missing assignments, you'll start falling behind the distribution, and 1 assignment probably wouldn't necessarily, it might, if you're on the borderline, it might make a difference of a letter grade assignment, but oftentimes it wouldn't. Missing a question or not doing well, 1 or 2, no, but we have so many. You keep missing several, and you'll start stratifying out into this category, and that won't be so pleasing in the end. Anything I can explain about the grade distribution or how we got it or what it means? And you're welcome to look up your points and figure out roughly where you fall in that distribution. It's way too early to call it A's or B's at this point. All right, let's go into a brand new topic. Basically, last 3 lectures, we've been talking about the atmosphere and what it does to solve or mitigate or respond to, however you want to say it, the heat imbalance, because there's more energy arriving at the center at the lower latitudes than there is at the higher latitudes. Today we're going to look at its complement, the oceans, and we're going to see that the oceans is likewise a very complex system, and we're going to talk about AMOCs. And AMOC is Atlantic Meteorial Overturning Ocean Circulation, and it flip-flops. And there's always a lot of concern about it flip-flopping, because if you all of a sudden change an ocean pattern, it's not like the atmosphere. You're going to have some downstream effects. Well, you'll have downstream effects in either of them, but this is a different thing. The lesson is one particular time slice, about 8,200 years ago. It's a fairly small geological event in many respects, but it is something that shows this happens. That's why we're going to focus on it. So we're going to shift from the atmosphere to the oceans. Circulation is again key here. Are there circulation patterns static? Shorter answer is no. I'm going to show you an example of it changing. This is kind of like the old fable of the tortoise and the hare. There's a race on, right? And you're trying to move energy from the equator to the high latitudes. And so you have Model A, the atmosphere, who's sleek and dashing and fast, but can't carry a lot of weight. Or you have the tortoise, the ocean, which is big, lumbering, but carries a lot. So I mean, if you think of those analogies, specifically it's the heat capacity. A volume of air can't hold nearly as much heat as the same volume of water. But the atmosphere moves fast, the ocean moves slow. Okay? So let's delve into this, and let's get some definitions out of the way. What we're going to talk about is we've got two terms to talk about the way things move on the planet. And there's meteorial, I can't pronounce it very well, but meteorial, which means basically things, or conceptually, or frameworks plotted around the globe through different longitudes, but at the same latitude. Longitudes of these lines, latitudes of these lines, there's the equator, the center line. In contrast to going around the globe, we have meteorial. That's a zonal flow, excuse me, going around this way. These are the same zones. Meteorial is the converse of it, going north-south. We use these terms to conceptualize the AMOC, and I want to make you aware of it, and then we can have a thought question about it. Which way which property would it be easiest to describe the atmosphere? And I'll ask the gentleman in the blue here. Yeah. Do you think we would talk about the atmosphere going around the planet this way or this way?
Up and down towards the poles.
Up and down towards the poles. Well, the circulation belts, though, go which way? Around. So the atmosphere is something like this. I mean, it keeps trucking around the atmosphere, goes over the lands, goes over the continents. They differ in the wind directions as belts that go in different directions. Now, what about the ocean? Which way do you think we're going to talk about this?
From south to north and north to south.
And that's the obvious answer, because I've set it up two one way and the other way. So yes. And why is it that the oceans are only we're going to talk about going north-south? Primarily.
Because it's from east to west. There's like land in the west, which is there's like a flat out straight line.
Except for a belt down between Antarctica and South America, the ocean currents can't go. They can go east-west, but they run into a continent someplace. Mostly the Americas and Europe. So by and large, then, the dictation patterns, so there's an interesting contrast, and one's going to work to move things around by passing it from cell to cell in the atmosphere, and one's going to move it around by moving up and down on the north-south axis. AMOC, the Atlantic, and it's related to the fact that this is a feature of the Atlantic Ocean, And it's a historical thing because the Atlantic Ocean is a big body of water, but people who study the Pacific Ocean call it a mud puddle. So that tells you something about the relative size. But it's the meteorology overturning circulation. And the medial means that it's going north-south. And so on this pattern, we're going to break this down a little bit, but basically things are north-south. But zonally integrated, blah, blah. So what we really need to think about is that it's a north-south property. Overturning, what does overturning mean? Gentlemen in, yeah, overturning. What is it? Ocean current overturning. Overturning.
It's like, it gets like flipped over.
It gets flipped over. What we're basically going to find is that this ocean current starts at the surface and then flips over, if you will, maybe not quite that way, but it sinks down into the depths of the ocean. And this three-dimensionality is quite different because the water is quite thick. It's not as thick as the atmosphere, but the atmosphere gets thinner and thinner as you go up, so all the action's right down close to the surface. The ocean's a little more complex, and so that's just to try to get it. And so this AMOC is characterized by a northerly flow of warm, salty water in the upper layers of the Atlantic, and a southward flow after it's flipped or overturned itself down into the deeper parts of the water for reasons having to do with what's called the thermal haline. We're going to explain what thermal haline is in almost the very next slide. The next slide says something about thermal haline circulation is the large, really large scale thing that drives the oceans, and it really is about density. We've talked a little bit about air density. We're going to talk an awful lot about water density. And global density gradients, and it's created because of surface currents and meltwater fluxes. And we'll talk about freshwater in a bit. But thermal and haline breaks down into temperature and salt content. Halite is the mineral that is actually what you think of as table salt. So thermal haline refers to some combination of temperature and salinity. And temperature and salinity are going to play a game like evaporation and precipitation did. The math is simple, but we're going to see that we can monkey around with that and change the way the ocean circulation happens. To get ahead of the story, the concept is that this is the part that we were looking at before, and here's the thermal haline solution on the surface, and then it overturns and goes deep, and it goes down, and then it goes around Antarctica, and it gets a little crazy here because of the circulation patterns. But we're going to see that you can actually potentially shut this off or reduce it, and that would be a flip of the AMOC. And we're going to do that at 8,200 years ago. The fellow that named this, Wally Broker, calls it the Great Conveyor Belt, the Great Ocean Conveyor Belt, the global, whatever you want to call it. This is the simplest representation of it. The ocean's currents are far more complex than that. We don't need to know that. I'm going to focus on the interplay of thermal, the temperature, and the haline, because they both change the density of the water. When you change the density of the water, you can turn it from something that wants to run around on the top versus something that runs around down at the bottom. If you want to flip it, you change this so that that either stops or enhances itself. So let's see, do we need anything more about this? Conceptual, it's a great thing to talk about. You'll see in here, there's a slight shading in the ocean parts of it, where the Mediterranean is far more salty than most of the world's ocean. Anybody want to hazard a guess at why? You know what? What do you know about the Mediterranean? You know where it is? In Europe and Africa, yeah. And then this was all that dry area, right? This is right next to it. What do you suppose is happening to the water in the Mediterranean Ocean?
It's drying up.
Excuse me? Because it's warm, it's going to evaporate more. So all of a sudden, we see a place that's high salinity because of evaporation. Now, it turns out that millions of years ago, the Mediterranean Ocean was low enough, evaporated enough that it dropped below and it wasn't connected to the Atlantic Ocean, but that's a different story. So, anyway, we see that there's a salinity difference. That's all great. I'm going to sidetrack to the 8,200-year event. I'm going to tell you what it is, and I'm going to argue fairly briefly that it is an example of the AMOC getting whacked or shut it down temporarily. And then we'll look at the implications of that. We'll spend more time worrying about the fact that that induced climate change than we will worry about exactly how it happened. So to get into that, this is a graph that we haven't seen before, I don't think, but I need to explain it in some detail. So this is today. Time is running from the distant past into here. We looked at these graphs over millions of years a while ago when we talked about sensitivity. Now we're zooming into only about the last, on this graph, about 17,000 years. Basically, this is the end of the last ice age. Out in here, temperatures are cold, warm. This was the ice age back in here. For our purposes, not much is going on. The world decided to hiccup in here, get warm, got cold again, got back cold again, then hiccuped again and got warm, and then went into sort of modern conditions for the last 10,000 years. In a separate session, we'll talk about this hiccup, or in a separate unit. But today our focus is what seemingly is fairly stable here, not the little last ice age, but the 8,200-year event. Now, these temperature ranges over 30 degrees at the center of Greenland are sort of a little bit of a slightly misleading. But if you wanted to wonder where global warming, the present global warming that's been around since I've been around, is on this, it's only about that much. It's very noticeable, but it's nothing compared to these warmings yet. Okay, I'm just estimating this. I didn't calculate it, but it's definitely noticeable, but it's sort of in the range of things happening in the last 10,000 years, even though it's outside of that range now. All right, the 8,200-year event was about 160 to 200 years long. It was cold and dry in certain areas. It did not have a global extent. And happened then. And this is shorter than the 1,000-year lower lake level. And look at Lake Huron and the wet period in the Sahara Desert. That was sort of a millennial, about 1,000 years long, roughly. I mean, depends on when you say it started and when it ends. But so we're talking about something that's a couple centuries, little blurb. A couple centuries, though, ultimately we'll find out that that mattered to some civilizations. It's a regional event. It's more known for its temperature, but it's focused on the North Atlantic. And these are the places where it got colder during that time frame. Places down here where it got warmer, and then a lot of places where it didn't really care that the 8,200 went. So it's more regional. It's not a global, therefore it's not a global energy balance change. But we redistributed the heat because the ocean circulation changed. So we changed how it was distributed. Therefore, we changed not the total global energy, the local energy balances. Precipitation has a more complex pattern, but it's regional. Some areas got dry, some areas got wet. The dry, wet, dry patterns kind of come around. Now, this isn't a comprehensive, every record, we don't know a lot about here and here and here, so it would be more dots, but this is, the take home here is certainly colder in the North Atlantic and regional precipitation patterns. So far, so good. Questions on that? Lady with the orange, whatever they call those things.
I don't think I have any.
Excuse me?
I don't think I have one.
Don't have a question. Anybody else have a question? Okay. The 8,200-year event is somewhat subtle. I'm going to get to the cause in a minute, but for now, we'll talk about how it's expressed in some of these records. Not every record shows it. These are a series of proxies. This is time going the other way. This is 10,000 years ago. This is today. So they flipped it. But there are various isotopic, sea surface temperature, biological, isotopic again, and then something really fancy that track various aspects of the Earth's surface. And so for this particular one, which is an ice core off the top of Greenland, it comes along, and then boy, that's when it really did something. And then it went back. Okay. This one, whatever this is basically something about the stackable silt. It's the amount for two different places, the amount of silt the oceans could care less about the 8,200-year event. This one, which is a bug that lives in the Arctic, or a foram that lives in the ocean in the Arctic, it felt it. This one, not so much. This one is a subtle one. It has to do with the strength of circulation. This is a chemical reaction that takes place inside the seawaters, and the folks that study it would argue that this little blip here is the signal of shutting one of these ocean currents off. Doesn't look very impressive on a graph, but it's consistent with many other lines of evidence. So, the point is that it's far subtle, it's pretty subtle, shows up in some things. The pachyderma has to do with sea ice extent. And this is how strong the ocean is going, and it basically, the take-home message is that it changed a little bit here. Okay? Now, what caused all of this? We've talked about the Laurentide ice sheet, and that's the ice sheet that covered North America. We're here in Cincinnati, right about there. And as we've seen in a different diagram, 8,000 years ago, that ice sheet was shrinking, shrinking, shrinking. Sometime about 8,200 years in round numbers, this ice sheet had shrunk to cover Hudson Bay. Now, one of the things that happens when that ice sheet shrinks is because it pressed the land down, and because there are topographic barriers today. The water in here flows to the Arctic. The water in here flows to the St. Lawrence. The water in here flows to the Gulf of Mexico. Because there was this pressing down, the land warped. So what you had was an ice sheet over here to the left, my left, and you had land down here, so there was the water that melted from the ice piled up in front of it. So shown in blue here is something called Glacial Lake Agassiz. It's a big lake. I should have calculated that, I didn't. It's a big lake, it covers quite a swath of Canada at some point. So it's a large volume of cold, fresh water. Thermal haline is about temperature and salinity. So you can see where we're going with this. We're going to say that this mass of ice that was holding it in actually catastrophically decayed. This thing is getting thinner and thinner. It's holding in against the water pressure, and at one point the ice sheet basically, or parts of the ice sheet, popped up and started floating, and the water scooted underneath it and discharged into out through Hudson Strait into an area south of Greenland. Okay? Gulf current, the currents come back. This area is showing up in a lot of maps. This particular, so that catastrophic lake drainage then spit out a bunch of fresh water. Not a bunch, but gobs. There's another graph we're gonna talk about, how many discharges of the Amazon. And I should have calculated that, but it would be several times the discharge of the Amazon. All right, it happened and was over in a blink of a geological eye, longer than our lifetimes. Where do I want to go? I think this is better explained on the next slide. This is an area that people have studied with computer modeling and have determined that because this is where the thermal haline circulation broadly overturns, it's sensitive. So this is a fancy metric called a stream function, which I'm not going to define for you, but it basically says this area is sensitive. If you want to mess around with ocean circulation, this is where you want to impact. And guess what? That's where the water came right into. So this whole exercise geologically, it was recognized there was big flooding here 30, 40 years ago. We didn't understand the implications, but we've used this case history to really understand a lot about how ocean circulation happens. So now it's a pretty much accepted hypothesis. And the take-home message is it got whacked, but the ocean didn't stay down for long. It came back and resumed its normal thing after the 2 centuries. Okay, but nevertheless, that's what we want to chat about. How do we whack it? All right, back to all about energy. Applying to the fluid called the oceans now instead of the atmosphere, where we've been before. We got that gradient from the low latitudes to the high latitudes. It's got to move. The atmosphere is off doing its thing. The oceans can't go that way. So the fluid so we did that. The ocean's a little different than the atmosphere. The atmosphere is actually drives a lot of its heat because it's heated from below like the tea kettle. So we got these great convection cells. The sun doesn't shine on the bottom of the ocean. So you can't heat it from the bottom. You can heat the top. But if you put a heat lamp on a kettle of water that you wanted to turn into tea water, it wouldn't work because the hot water would stay at the top. The heat would all stay at the top because why? As you heat it up, it gets less dense. That's great if you're going to come from the bottom and you want it to go up. If you heat it from the top, it's not going to set up a convection belt. So the ocean is heated from above. The atmospheric winds do play a part in the ocean circulation because they do interface. They do go across the ocean and they make waves and all that kind of stuff. So they set up a surface circulation. The very upper stream of the ocean is driven by the interfaces with the atmosphere and follows the atmosphere. And I'll show the patterns of that in a bit. There's the fresh water that gets into the ocean. It's fairly small compared to the volume of water in the ocean. But it comes off the land, it comes off precipitation, and one of the worries is it will come from melting ice, so the existing ice sheets that you've probably read about doomsday scenarios that invoke the melting of the ice to turn this ocean circulation pattern on and off. I forget what they call it in the popular press, but I'm sure you've heard of, or seen it someplace. But now this is the thermal haline circulation that we want to delve into. Back to modification. We saw this in the last lecture. It had to do with why there's excess energy there, and in fact you have to move it out. Anybody need a refresher any more than that and that? Good on that for now. Okay, and what was this graph from last week? Or last unit? A little thing with a nice reddies down at the equator.
The ITCZ.
The ITCZ as expressed in this case by the precipitation patterns. So that's just where all the rain is. Okay, so if I think about now the energy balance in a slightly different way. I go from the North Pole to the South Pole, I have the equator here. I see that precipitation by and large has a peak right there at the equator, and it drops off quite rapidly, as is here, drops off rapidly, goes to a low, takes another bump, and then goes down because it's too cold for much precipitation at either pole. So I can explain the precipitation pattern fairly nicely. And the thing that's weird about it is the bump in the middle. And so why would there be a bump in the middle? Why is this red band restricted to a fairly narrow area, high rainfall? Why is it a high rainfall? And we're talking about roughly 2 meters of precipitation. That far from the floor, precipitation a year. Water. We get half of that here in Cincinnati, or less. Why is it so wet here? It's hot. Evaporation on the ocean surfaces sends a lot of moisture into the air. What happens to it? Does it get carried away from the center part? No. A lot of it just goes up, falls right back down. Up and down, up and down, up and down. So that's why there's a spike here. Some of it does get transported away, as we talked about in the homework exercise. So that pattern makes sense. We get in here, and we get in the Hadley cell influences with the high pressure and the low pressure and all of that, and we get lower precipitation, a quarter of what it is at the equator. Now, the other one, the evaporation is not quite so obvious. That's the blue line. I suspect our initial, gentleman in the hat, what would be your initial anticipation of what the evaporation is right at the equator? It's low here relatively, but is that what you would expect?
I would expect more at the equator because of the warmth.
You'd think because of the warmth that the evaporation would sort of peak up here, and then it would just get lower and lower because of the coldness, right? But this is one of these interplays. Because the evaporation does send moisture up into the air, it can only hold so much. So it shuts it off, and then it rains back down. So there's a certain amount that you can actually put in the atmosphere. And basically, it's exceeded because of all this rain that's right there, so you can't get any more. So there's a drop in the evaporation potential, even where it's the hottest. A lot of climate systems got these two things operating in non-intuitive ways. But then evaporation peaks out, not quite, but sort of where the rainfall is the lowest, like these areas, and we get low precipitation there. Okay? Gentlemen, way back. Where would I expect with this evaporation pattern to see the most salty water? And why am I asking, how do I connect salt and evaporation?
When should you expect to see more, less salty weather or wherever there's the least amount of precipitation?
Wherever there's the least amount of precipitation. Okay, but how do I get, so I can dilute the salt water with rainfall, which is fresh water, right?
Yeah, so where the most
Okay,
precipitation.
how else can I get salty water? If I take a big half a box of, I got a pitcher of water and I take a half a box of table salt and I dump it in there and I let it set for a while, what's gonna happen? The water will evaporate. First of all, you can stir it up, it'll dissolve, right? So I've got salt water in my pitcher now. And then what will happen? Over time, that water's gonna evaporate, right? The water will go away and dry up. Well, where's the salt go? Does the salt go with the evaporated water? No, the salt's stuck behind whenever the evaporation takes place. So with this kind of concept, where would I expect to find the most salt? Well, 30 degrees on either side of the latitude. Those where the salty water, that's where the evaporation processes should, by and large, make more salty water. It's not exactly that simple, but that's a starting point. So we've got salt now. Okay, let's delve into this a little bit deeper. Sidetracking just for a bit, I mentioned earlier that the wind patterns actually drive the ocean currents at the surface. So here's basically a variety of ocean currents with different names that have a cell, a rotating cell, that is driven by the wind patterns. And so the wind patterns here are like that, the wind patterns in this area are like that. There has to be a return flow. This is a warm, this is a cold, this is a cold, this is a warm, warm, cold, following the general directions. And most of them make some sort of loop. In this case, the California cold current is paired with, can't pronounce the Japanese name, but all the way across the Pacific. And on it goes. So those currents, pay attention to the land boundaries as we talked about, with the exception of around Antarctica where the current just go around and around, because the wind goes around and around. And there's a countercurrent in here. I don't know if we need to get into that too much. All right. So let's zoom in on the ocean circulation this morning. And the ocean circulation this morning is shown by these streamy things. It's kind of diffuse in here. It's really up through here where the Gulf Stream is from the US. Comes out of the Gulf of Mexico, and it's meandering off to here. Now this morning, there's a couple of oddball things in this image. Those are the hurricanes that are in this South Atlantic today. South Atlantic's really down here. This is, what is it, lead that's gonna whack up here, and I forget the name of this one. So the currents in here are a little bit masked because it's a big storm. These hurricanes are doing their part to move energy from here to here. They're picking up warm water, they pick up some moisture, they swirl and swirl, and then they dump it, and they keep whirling around, and then they dump it up here. So that's fine, so that's a bit typical, but there's eddies in the surface current. In other words, it's not a simple line of, we talk about the Gulf Stream, we think it's a sharp line. But back in the old days, the folks that were going across there in sailboats worried very much about the Gulf Stream, because if you get into something that's moving a couple miles an hour, and you're only going 4 or 5 miles an hour, it'll take you away from where you think you are. So if you're just going across the ocean here, and you think you're heading for the Virginias, and you get into the Gulf Stream, you gotta do a little correction for the fact that the water's moving the other way. So they always carried a bunch of thermometers around with them to measure the water temperature. Oh, you're in the Gulf Stream, start a correction. Whoops, we're out of it, change the correction. So pragmatically, we know something about this because people measure it all the time. All right, what else do we need out of this diagram? Anything else out of this diagram?
I'm seeing the Gulf Stream tail off more like due east than continuing up towards Greenland.
In today, yep.
Okay.
Seasonal effect, daily effect. You're not gonna change the position of the Gulf Stream long-term. This is not to say there isn't more activity here, this is just where the fastest is. Now during the Ice Age, that was one of the things. The Gulf Stream we think of as going up here, and here's the sort of the warm water that's tucked in here. And so we think about these areas which are pretty high. You know, London, England's quite a bit north of us, but it has a very similar climate. And they generally attribute it to the fact that it brings warm water up here. That's fine. But during the Ice Age, the Gulf Stream did look like this pattern. I was kind of amused to see it expressed today because it went over here, so that kept everything nice and cold up here. Didn't bring any fresh water up. That's a longer term problem. We want to get the warm water up here into that zone where the fresh water came out and whacked it. But we'll get there. All right. The other part of this is the sea surface temperature itself. Pretty colors, reds, colder, thinking about ice forming, starting, it's fall time. It's cold at these latitudes, we're gonna get some ice, and some intermediate temperatures here. And like we just discussed, the really warm belt seems to be trending a little far south than we would normally expect it to be. I want to point out that this is a fabulous picture of things, and we see here's where it's really hot, because you're close enough to the equator to get all that's in there. But the surface area is only a couple hundred meters deep, which in the grand scheme of things is not much. A lot of water, but it's sort of small potatoes for the ocean. All right, surface currents and temperature. We get where the heat really moves around is in the deeper currents. And I'm going to try to simplify these so we don't get into the really deep, into the nitty gritty of it. But the deeper currents are quite a bit more complicated. They're not driven by where they actually go is controlled part by the boundaries of the continents and submarine. This is the Mid-Atlantic Ridge. It's a high topography, and those things control these deeper currents. Keep in mind that the oceans are almost 4 kilometers deep. A lot of water. Excuse me. They average 4 meters, 4 kilometers. Deepest spot's 30,000 feet. In other words, same kind of height. That's higher than Everest is. So you drowned Everest by a couple 100,000 meters, actually. The basin shapes that they operate in are fairly complex. Those are not simple geometries. The Earth spins. There's something called the Coriolis effect. As the water tries to go around, there's something that is, besides the wind energy that's driving it, it's called the Coriolis effect, and that happens. But who wins the day after all these things is the density. We're going to talk about the oceans being a density-driven current, and density is going to be the product of haline, thermal, and temperature, and haline. And density is obviously going to go from low to high. The same principle that we talked about with the atmosphere. If you're going to have hot water, is going to tend to rise. Cold water is going to sink, right? That's pretty simple. How do we actually get the values of that then? So coming back to this handy-dandy diagram, let's see if we can speculate if there's any cells. This is a cross-section through the ocean. This is a thought exercise. So this is a line through here someplace. It goes through the equator, goes to the north and not quite to the south poles. And based on this diagram, how would you set up the deep convection? This is the depth of the water from to the average of the Atlantic. How would you map the surface density? What's the surface density? Partly precipitation, evaporation, they map out. Are we going to get any convection cells? Everything else being the same. What do you think?
It's just like a line.
Would be a line. What's going to drive any convection cell?
Atmosphere.
In the atmosphere, it's driven by the atmosphere displays a lot of convection cells, but what drives them? We started at the equator and we heated up the air, and what happened to the air? And the air rises because it's less dense than underneath it. All right, so what we want to find out is, can we do the same thing in the ocean? Can we set up something here that will set up some convection cell, some configuration? Maybe it's one cell, maybe it's nothing, maybe is there anything? Is there any, anybody want to make a suggestion? The lady in the blue shirt?
I don't know.
How would you start attacking the problem? If this was the homework in your, I made a deal that if you could solve this problem, I'll give you an A and you get out of the rest of the class. So you have some motivation to do it, hypothetically. How would you go about solving the problem? This is just a conceptual exercise with just this piece of information. This is not go out and research and get a whole bunch of more data, because that'll confuse the issue. man, getting out of the rest of the class is worth quite a bit, right? Where's gonna be, what's the relative balance here between these things? So right here, how much precipitation do we have? 200. What's the evaporation? Call it 150. Net loss or gain of water?
Gain.
Excuse me?
Gain.
Gain? Fresh, or is that gonna make the water that falls in the ocean fresh or salty? Fresher or saltier?
Right.
So all of a sudden, we could say, here's a belt of fresh water, fresher water. Where's gonna be the salt? The lady in the white shirt next to Bass Grove, where we just discovered that this would be a good area to get what?
Pressure water.
Fresher water. Where do I wanna find the area that's gonna be the most salty? How would I use this balance to find out where the salty area is? Where? It's gonna be on the surface. This is all the surface. So I got fresher water here, less salt. Where's gonna be the saltiest water? Where's the, what do I wanna look for? Evaporation, precipitation, or the combination? I'm gonna look for the precipitation, but also I need to think about the evaporation, because that'll take the water away. So what's going on right here? More evaporation or more precipitation? Well, the precipitation's the red line, about 50. Evaporation's 125 centimeters, right? Is that gonna make the water right there fresh or salty? Gonna suck the air out, you're gonna suck the water out, net, you're gonna take it out, what's gonna happen to the salt? Is the salt going away? No. So where's it gonna be saltiest? Where's another place that's gonna be salty? Same thing over here. So here I've got fresh and salty. Can I set up a convection cell that way? So fresh and salty, which way would the convection cell try to go? This way or this way? Is the fresh water or the salty water gonna be more dense? Temperature the same, the salty water would be more dense. So the salty water comes down here someplace, right? Now what's gonna bring it up? I'm removing water here. Is it fresh or salty though? This is fresh water, right? More or less dense. This is gonna dive down. If this dives down, this is already high or low density. Lady with the white, whatever those things are.
Low density?
It's low density because this fresh water effect takes over. So I get something that's going down here. How does it get back up? This is low density. I've got dense water coming down, and I got less dense water here. Can it come down and back up?
I don't know much then.
The dense water is gonna go down because it's denser than the stuff underneath it. That's all good. Geez, that's gonna pile up here. Point is, it can't, like the air, had that cell we closed. You can't do it in the ocean that way. You effectively have to think about some other circulation patterns that might go to the high latitudes where things aren't so active. It's a thought exercise to show you why the surface, why the fundamental difference in the circulation patterns. Okay, so we want to stick with this density thing. We're going to do something different with it. So we're going to call it the thermal haline circulation. That's the current. This is a cross section. And this is actually in the Arctic. And what it's showing is a shallow area and a deeper area. And it's showing 3 different water bodies. This is schematic. It's also showing our friend the sea ice. Now, sea ice is not a wild joker in this. Sea ice is also an important thing in this. Because to make ice, you get rid of the salt. We've talked a little bit about salt melting ice. And so if it's cold enough, it'll melt the ice will form anyway. But what it does is it gets rid of the salt, ejects the salt, doesn't allow the salt in the ice crystal. So you have this area here where you're forming ice, and you've got what? Salt is released, so you've got a higher density all of a sudden. Where is higher density material going to go on this surface? The lady with the green, whatever you call it. So I've got a localized, fairly shallow water here. It's making salty water there. Where's it going to go on this diagram? It's going to go out, and it's going to seek a place it can go as far down as it can, because it's the densest game in town. And so it'll end up going off the deeper topography here. And so, but it doesn't go all the way to the bottom. It gets diverted into kind of a zone, a middle zone. So all of this salty water then somehow doesn't get to the very bottom. That means that something else takes bottom. That means that this thing is more dense than this water. It didn't get down through it. And if we read this at sort of 200 meters, it's warm, salty water. Warm's not good for density, salt is. So this density contrast then doesn't, this shows us basically that we can stratify fresh cold water because we've made this ice. We've got the cold saltier water, and then we've got a warm, really salty water. And they have different densities. Okay, any questions on that? And we're going to get to a diagram that explains this relationship, and we want to keep in mind this density. Density, density, density. If I change the salinity up, it takes the density up. The water mass sinks. Change the temperature up, the density goes down, the water floats. That's true as long as the temperature stays the same. This is true as long as the salinity changes. What if you start messing around and changing both? To just elaborate and then forget about it, here's a cross section. Here's the North and South America. This is where our Gulf Stream is coming out, and then in this diagram it's coming out of the board. But we've chopped the world in half. What we're seeing is the bottom of the ocean, greatly exaggerated. And one of the things we see is here's somewhere some water's coming down. This is the overturning at the end of the Gulf Stream, coming down in here, on its way and coming up near Antarctica. But there's cold water from Antarctica coming down that goes underneath it. And then there's the Mediterranean water that's just coming out of this here, which is salty but warm. And then there's something in the Antarctic conversion, which is middle water, intermediate one. The point is that there's quite a complex three-dimensional geometry to all these ocean currents. Second point is they're slow, they're turbulent. It takes something on the order of a millennium and a half for these things to complete a cycle. So it's one of these things where there's a choo-choo train going. It's going at a certain speed. It's moving things, but you can't stop it. It's moving them slow. And we want to think about 1,000-year cycles here. So changes in this ocean circulation to do something in only 160 years is pretty impressive. We're going to do it at the surface. We'll talk about deep ocean, impacts of deep ocean currents a little bit later. All right, this is the diagram we've got to understand to get further along. Two variables. Salinity, these are the salinity units, and temperature. The lines are what we call contours or they're lines of equal density. The water is is that this line, on this line, the water is 1.0265 grams per centimeter. So a thing that's basically the size of, I don't have anything that's about that size. Half of this piece of chalk weighs a little over a gram, which isn't much. All right, the funky thing about this is the lines aren't straight. So what this is telling me is I can get this particular density by changing, how do I get that density? At this point, this density and that temperature give me that value. This point, it takes that temperature, warmer temperature, and more salt to get the same thing. Makes sense. More salt makes it more dense, temperature changes the other way. All right, now, got a green shirt in the back. Which way does, these lines are all this, anywhere in that line is the same, but in general, if I move from that corner to this corner to that corner, am I going to more dense or less dense water?
You are going to less dense water.
Less dense. Here's the densest water, 0.202928587575. So less dense water is up here. So if I introduce water here to a water mass there, less dense. If I put it in the bottom, I put some water of this density underneath this, what's going to happen to it? Almost got everybody. What's going to happen to the, this is going to be more or less dense, right? I'm going to put some water underneath this. Is anything going to happen to it? Denser, less dense. I'm going to put the more dense under the bottom.
You mean more pure water?
I'm sorry?
More pure water.
It'll do-
What is that? Put some water here.
These are the weight, the density of the water.
Yeah.
And this one's more dense than this one, right? So I have a jar of this stuff, and then I put a jar of the less dense stuff on top of it. What's going to happen?
It will drop.
I've got dense on the bottom, I put less dense on the top.
And we're going down. The jar will go
The
down.
less dense isn't going to go into the more dense, is it? I asked it the tricky way. If we inverted it and I put the heavy water at the top, or the more dense at the top and the lighter at the bottom, then it would flip over, of course. But if I start with the less dense on top, doesn't care. There's no motivation, there's no driving force to change this. So, water, if you're gonna go from here, if you're gonna go along this line, these water bodies are gonna have a tendency to be less dense, more dense. They'll stay, anything up here will stay on top of anything down here. Or you can flip it, anything down here put on top of this they'll circulate around. Okay, now, there's red lines on here. So here's two different situations. They both have the same density, right? Okay? And so I've got to get to points, this is point A, point B, and point C. How can I get to point C? Is point C more or less dense than this line?
Is a little bit more.
80, 75.
It's a little bit more, I think.
It's a little bit more. It's more dense because it's this way. Okay. So how do I make, out of water that's this density, how do I make something that's a little more dense? That's what this graph will help us find. And if I started here, and I evolve this water body to get to here, what's changing from here to here? what's the temperature and salinity right here? Temperature, 9. Salinity, 35 something. What's it over here? 5. So what happened to this water to go from here to here? The temperature went down and the salinity went up or down? Excuse me? Down. So both things acted sort of in the same direction, but one of them had to take over because it's not on the same line. Right? So I changed the density just a little bit. That's enough. That kind of density is what drives these ocean currents. Just a real small difference. Changing an ocean current from 5 degrees, 10 degrees to 5 degrees is a lot of temperature change. I don't have as intuitive feel for these salinity changes. They don't seem like much, but they must be. Okay? This graph is an important part of your homework. Questions? Free floor. Everybody has a chance for a question. Maxine, question.
I have a lot of questions, I just don't know what.
Pick the best one. Let's start with that one. Can you walk me through what this graph is about? There's 3 things on it: temperature, salinity, and density. Right? And they're related. And this is about what? What are we talking about here? This is with seawater, right? Okay. And so seawater is salty. And so if I go swimming in the salt water, do I have a tendency to float or sink? Or you or I, both of us?
Sorry, can you repeat that again?
Yeah, if you or I went to the beach and on the ocean, and we went into the water, would we have a tendency to sink or swim because of our density? We float.
Swim.
Salt water is more dense than the water in our bodies is mostly, our body's mostly fresh water with a few bones thrown in. But the general tendency in seawater is to buoy us up. So the dense stuff is denser than we are. Okay? My natural buoyancy does float in salt water, but it doesn't in fresh water. I'm right in the balance right between it. I've got big bones, so I sink. That's okay. You would float, I would sink. So this is about density because we're trying to drive the ocean to do something, overturn, go from the top to the bottom. We can do it with this density graph. The graph compares 2 values, salinity in some units, and temperature. You'll see other units out there if you went out in the literature. But you can evolve a water body to get to a different density a couple different ways. Monkey around with the temperature, but you also have to change the salinity. If you change the salinity, you also have to chop the temperature. That's what these going from A to C or B to C does. Clearer? A little bit? All right, we're almost through. Let's see where we're going. Okay. So now we're going to sort of set anything else about this graph, because I'm going to set up where we've got some data that I've plotted for you. I'm just going to set up where that's coming from. I'm not going to introduce any new concepts now. This graph this will drive us a little bit nuts here for a while. Possible changes. This is an example of the gentleman said, decrease in the temperature. Excuse me, increase in the density. Okay. So if we go back to the ocean and we look at the density of the ocean on average, we see that the lowest densities are here at the equator. The highest densities are up in the North Atlantic. We see low densities, we see intermediate densities here in the, this has got to be a different unit than that other graph, down here. So what this is telling me is a lot of action because there's differences between the equator and the pole. Now, this overturning point, and that's the whole point of the 8.2 event, and that little bullseye that was on the graph, is of intense interest because not only does this come up here, this is also where water out of the Arctic drains. Not only that, is that the geometry goes from really deep water to shallow water here. So there's been an intense set of investigations about the water properties in this part of the world. It's called the Irminger Sea. Okay? And so there's into the wild, the Woods Hole Oceanography Institute talks about an expedition they took up there 10 or 15 years ago where they ran into 40, 50-foot waves and bad storms and stuff. And they made, plotted up how good of heroes they were to get this done. Up in this area, they've been able to instrument it over the last several years, and they have various kinds of instruments. Basically, they stick a weight on the bottom and they put something on a float, and then they put a bunch of thermometers and things in that, thermometers and density issues. They put them at different depths. They also put buoys out here. They get whacked around by the wind. And more lately, they've put drones in the ocean. And the great thing about the drones is these get you something, what's happening at one depth. The drones will take a path up and down, and they can get information over the whole depth. So the point is, there's a lot of information from this area by these techniques. And if we take one of these, and you notice there's a little offset between the ocean and the top, and we plot it up for a couple of years, this is the real raw data. There's two things there, temperature and density. No, three things. Oh, good. Temperature, salinity, the density. And I've put in two densities at different depths. Density, density. And these are real numbers. We're going to interpret these real numbers in terms of that diagram. So, the first thing to think about, and this is time, and there's a little over 2 years of time here. 1 year and another, and you can think about this as being January. So if I were gonna ask you right off the bat, what, at 180 meters deep, what's the density over the period of these 2 years?
1,020 and a half.
128.5, and does it change?
Not
It's
so much.
duller than beans, right? If on the other hand, I look at the density only 30 meters deep, it's almost time to go around the whole circuit, right?
Anywhere from like 1,027 to 1,028.
These are plotted on the same scale, so this density varies over the course of time. Well, isn't that interesting? How does something 100 feet underneath the ocean surface, 30 meters under, well, it does. Fair enough, right? So, what's the salinity doing 30 meters down below? Excuse me?
It's varying in certain times of the year.
Certain times of the year, it varies more than other times of the year. That's probably related to sea ice extent. Does it vary a lot?
Not normally.
No, I mean, on average, it's sort of a stable number, but it has its days. And those aren't necessarily storms coming through because with 30 meters below the surface. So if we thought about the temperature and the salinity, we should be able to go back to that graph and get what the density is. On the other hand, we could take the density and sort out whether the temperature and the salinity. So the graph that we just looked at to solve it, here's the real data. A homework exercise is more about analyzing the data than it is coming up with it. We're ready to talk about that. Any questions on this? This graph is available. You've got this graph. and you've got the other one. So, questions? These are all kind of short answers, and this is for the Erminger Sea, right in here. This is that hot spot of activity that the 8.2 event. We've delved into oceanography. We're going to delve into oceanography deep like we did with the hydrological balance. We'll immerse ourselves from the density currents on Thursday, and then next Tuesday we'll talk about the implications of this changing of this monkey's balance. We're going to find out. Temperature vary over the year. Well, those are pretty straightforward. That should be doable. Anybody doesn't see a way to do that?
Which time of year specifically
Oh!
would we be looking at?
Well, don't you have to specify, and then you can do it whatever you want?
Okay.
Or you can take the average. You have to tell me, you'll have to justify which choice you do. So there's a slight trick to that, but it's not insurmountable. Do they agree or not? Doesn't have to be off much before it actually would matter about the circulation. And then the age-old question, given those density that you found and the density measured at the deeper water, is it gonna overturn or not? Binary thing, you can flip a coin, get an answer. So this tries to integrate all of the concepts that we get today, and once we get this exercise done, we'll have a good time about it. Then this is go out and find on the internet something about tipping points, because this is the threshold effect or the tipping point. And the tipping point of the AMOC, and there'll be all kinds of those papers, and just give us, describe that link. Find it and read that little blurb. You'll see all kinds of these. I mean, I know figuratively, hundreds basically. And some of them are based on real science and some of them are fabricated. If that's okay. Questions before we adjourn? Yes?
I don't think that this is available on Canvas.
Can you check now again? It should have come online at 2. Did it or didn't it?
It says this file is part of an unpublished module and not available.
Okay, so with our new TA, who's brand new to Canvas, he set it up, but he didn't turn the published on. So I can do that in 2 minutes. Thank you for pointing out. I will ask if you find some things a glitch, and he'll do things a little differently than Liz. So we're all gonna learn to redo things. But yes, turning the publishing on would never, it's one of those tricks in Canvas. Yes, ma'am?
Are we just using the previous graphs on the previous slide?
Yeah, for this exercise, you want to understand this graph, but the question refers to that data.
Okay.
I mean, it's real data. Okay? All right, sir.
The numbers are different from the density, like that's 1,000, the other one's 1 point something. What do we do about that?
Really? You're gonna have to do unit conversion? I'll have to publish it.
Yeah.
I think you could quantitatively figure it out.
Yeah, I mean, I'm sure.
No,
I just didn't know if there's a
the density is in 128. No, that's 1.028. That density is right here.
I think it might just be multiplied by 1,000.
Yeah, it's
Is
the
it-
same
okay.
number, it's
I
definitely
was,
one.
okay, I was making sure.
Yeah, okay, good eyes. See you on Thursday. All right,